Good evening, everyone. Let's see who's here. Sorry about the late start, but, well, I had to finish fooding, and that took a bit longer than I anticipated. So, today's plan, now that I have this here fun virtual machine working, or theoretically working at the very least, is we're gonna go and try and single-step debug the board and what the hell's going on inside the clock code, because yikes. Once that's fixed, we'll then see if the UART is going to behave, and then go from there. See if we can figure out the USB debug problem, and yeah, you get the idea. This is going to be interesting for me, because I haven't used these tools in quite some time. 11, maybe. Indeed, keyboard party. Not sure why it's not. This is going to be annoying. So that add with carry is correct. It's also unused. We then have... yeah, this is init. Oh, so if I remember to mute my phone. Unfortunately, we can't do this with source, so this is going to be a lot more tricky than I would like it to be. So that relative jump there is in the middle of the data copy loop. I should really show you what I've got on the other screen right now. Take a second to get OBS configured. Terminal. Perfect. So this is what I'm currently looking at, and this is what I'm currently trying to debug. Oh, I've just noticed my chat overlays aren't working. Guess who forgot to rebuild OBS after an upgrade? Yeah. I'm kind of sort of on Windows, but I'm not. The debug tools only work on Windows. However, I'm running it on a virtual machine. Yes. Big stinking virtual machine. So... what I'm currently looking at here is the disassembly of the code that is on the board. We can see here, for example, this line is the call over into our main, get everything started up and going and happy. Which is apparently a call to address, well, my right hand side here says it's address 2C0 and the left hand side says 160. Arguably it couldn't really be that much worse. This is pretty bad. So this looks to be the line where we jump into the actual firmware, and that line right there should be the first line of the real firmware. So if we continue, yeah, it's continue, F5. Cool. That was nice and fast. Okay, so we are now in the firmware itself. This is where things get interesting. It's based on Visual Studio. It does not run without DirectX and a whole pile of other shite. It sucks. So 29D, let's go fish for 29D. Welcome, Amy. No, I have not switched to Windows before you ask as well. This is a virtual machine. This is the only way you can run the tools. Uh, 53A. Yeah, so these instructions here are the start of the function we want. Hey Derek Boom, welcome. Well, so the thing with these tools and how bad they are, because this tool is really bad, like I cannot do source stepping or anything like that. This is gonna hurt to do tonight. Is I have a Glasgow. I have a board design that allows me to interpose it onto my keyboard. With full signal integrity being kept where as much as possible. And I have the motivation, shall we say, to want to try and fix the fact that you can't use GDB on this. Because I wanted to be able to do source stepping, but the newest GCC that this toolset has is 5.4.0. And for those of you who know how the GCC version numbers work, know that that is old. So I really want to get the FOSS toolchain able to interface with really it was the only cheap at the time blend I could find of enough SPI buses with DMA, quite importantly, that also did USB at fast enough speed and had enough IO channels of the right kind to drive a key matrix. And I kind of stuck with it at that point because I knew I could make this work. Yeah, It wasn't around back then, and yeah, it's a thing. Yeah, well, one day. Maybe. Oh, bollocks, we just skipped straight past the thing I'm trying to break on. Well, we can still look at what happened there. So, PLL enable, bit 4 is currently set. That's the... this is where I need the data sheet. Yeah, well. Yeah, that one even. Hey, I'm an FPGA person. Watch it. Oh, no, that is the wrong folder. I want to be in docs. Also, I will point out this, if nobody ever bothers to use these tools, then nobody ever goes and fixes the fact that they're broken and that the FOSS community is losing out. You know, if nobody ever uses this processor, then the situation never improves. So I guess a part of this is at this point that respinning the board with a new processor that's lower cost and more suitable kind of isn't actually cost effective for me at this point. Yeah, exactly. If nobody ever bothers diving into the problems, then they never get fixed. Oh, it is. But it also would mean that a lot of the stuff I'm dealing with right now wouldn't be a problem. It would be a non-problem because it's all be dealt with in the bit stream. And we know that the tools are really good. We'd also know that there would be no latency issues and like I could do all kinds of crazy stuff. I would have other problems, exactly. I mean, a softcore though, Steffi, at this point, I have a more or less workable PIC-based softcore, PIC 16F88 in fact, and I could go and glue that, an 8-bit CPU, into an FPGA. And it would be fine. I've got the tools to debug it and everything, and they work on Linux directly. So you say, oh god, but actually it would be a really good solution. I don't need a 32-bit MCU here, that's the whole thing. Anyway, the thing I was looking for in here is... Up 5k forever, huh? It's this one, the system clocks. Not the system clocks, sorry. Is it? No. System control and reset? I've lost where it is. There's a section specifically for what we're dealing with. Aww. I saw that. That's really cool. Oh, I know why I'm struggling. I know exactly why I'm struggling with this. I need the other datasheet. This one. Bingo. So we're currently looking at the oscillator setup, So oscillator control register itself. Oh, right. Yeah, I keep forgetting this actually does have decode. Like I said, I haven't used the tools in a really long time. Oh, interesting. RC2 here is still enabled, even though it shouldn't be. 32 meg is enabled. XOSC is enabled, PLL is enabled. 32, XOSC, and PLL are all ready. Those look good. Let me just quickly check some decode values. So, value of, wow. Value of 3 in this field here, which is what we see, does indeed correspond to 12 to 16 megahertz. The XOSC cell bits here being 0 says it's an external oscillator, which is true. And gives us the fail flags. Oh hey, there are undocumented bits. What do you know? Those are supposed to be reserved. XOSC, FDEN, and IF are 0. And there's actually a PLL pair too. Looks like it's bits 2 and 3. So we can actually monitor for the PLL failing. But the datasheet doesn't document that. Oh yay! So then the PLL... PLL fac, that's the multiplication factor. That will be... I wish that said more about what that did and how it did it. Knowledge dungeons. I like that way of putting it. Divide by 2. Oh, I see. Clock source is set to XOSC. Good. There's another bit doing some heavy lifting that is not documented. Whether or not the PLL is being divided by 2 or not, it is not. And then there's a multiplication factor, which we've set as 3. I hate using the Windows calculator, but it's easier than switching things around in OBS. Yeah, so that should be getting us a 48 megahertz clock to work from. That's our USB clock. We kind of don't care about the DLL at all. So, OSC looks fine, interestingly. However, the clock registers here do not. These look actually rather wrong. That, for example, should not be all zeros right now. Which would explain why we are stuck even with a 2 megahertz internal reference clock for FPER. It should be 3. Oh, fun. Well, yeah, so I was actually just switching over to the code. This is what ran to get us to that point. You can also find this code, for the most part, on GitHub. I have most of it pushed. Give me a second. That should be the link. Yep, that works. The clock control thing. Right here. Yeah. That's in... Oh. Hello? Yes, indeed. Yeah, I was just scrolling up for the other. Trying to remember why I did that. Okay, for future compatibility, write these bits as 0, and then I'm selecting what source I'm using. That's exactly what I want it to be doing right there. However, what I'm thinking is happening is that because it's a protected register, the value we're putting in CCP isn't right, or it's timing out before we can get to this line. Let us switch back to the Windows VM and find out. If we go to configuration change protection, this has lyrics. So, for protected I/O registers, within 4 instruction cycles, oh yeah, the I/O registers thing is very annoying. So yeah, it should be the register one, which I think is what we're doing. What I'm going to do is I'm going to restart the board, which is that one right there. And we're going to run this through to where we enter into the routine that does all the clock changes. And we'll start stepping. So we're reading into... Doop-a-doop. These 2 registers here. Sorry, no. These 2 registers here, which is one of the memory access registers, sets. So let's read 2 values in from an I/O location, 3D and 3E. That sounds like those are from the oscillator, if I recall correctly. No, I don't. grab some source open. This isn't the live source, this is some slightly modified source from my attempt to try and make this build against the older compiler. It should be systemcxx all the same. Of course those are unknown identifiers. Give Windows a second to not do anything, apparently. Oh, that's frustrating. I know it knows about those, just... Let's go diving into my installation of the frickin' toolchain again. Megas, real X mega 256 A3U.H. There we go. That was the header I was looking for. So we just read the stack pointer. Okay. Loading some immediates. Those loaded into register 18 here and 24 plus 25. E, 0, 07, and 01. O1's there. I wonder what the other ones were for then. Storing direct with displacement. Curious. I wonder what these are loading. Why does this have to be so broken? That feeling when even the official tools are broken in very weird and fun ways. So hex 50 is the oscillator. That would be this one right here. So R24 holds where... No, usually the official tools are the ones that are well figured out, because they have to make money off of them. So hex 50, that is the address of the oscillator registers. So I'm betting I know exactly what it's doing. That's zreg. And zreg is being loaded with 0050 hexadecimal. Can I get it to display these as like pairs? Nope. Oh, but I can look at the... yeah. So those are being staged ready to go into ZReg, and this is the value. Yes, it's a Windows 10 virtual machine, which has been kneecapped so it can't hear me or anything like that. C0 is probably the value we're trying to write to the register, which, yeah, that would make some sense. I look at this in VS Code. Yeah, that value comes out to C0 right there. So we've just identified the line that does that right. Cool. Now the question I've got is, what's happening when we start trying to do like these CCP writes? Is it doing the dumb thing or is it doing a smarter thing? Actually, that file hasn't changed, but Windows is stupid. Yeah, so ZReg got loaded to hex 50. Is then using store with offset here. No, this is my Windows virtual machine. I do not run Windows Native anymore. I haven't done for some time. Like, several years. Nearly a decade. So this is doing a write to Z with offset of whatever is in this register. So this is how it's doing these register writes that we're asking of it. Which, if we check in here, we should be able to see that having just happened. Yeah. It's a lot of code that it generates for this. We're still trying to traverse down to this loop for what it's worth. Of course it won't tell me what that identifier is. 216. 216 in hex is D8. So let's scan down this code and find any instances we can see of hex D8. There we go. That is the first one, I think. So that's the CCP register being written. Cool. Which we've got to very quickly because the external oscillator's up and it's ready, and because we've been slow for it. So this is to set xosc fail 1. Which it does, just in time. Interesting. Z register all set for that. So we're now looking for writes to hex 40. So that should be the next thing that gets hit. And indeed, there's a write to hex 40. And that is offset 1. So it's this one. That actually is correct, I think, because if I recall correctly, those two constants are zeros. Yes, that was setting the dividers up. Now this next one's the one where it should change stuff, and we should be writing 3 into the control register. So we do the unlock. There's our 3. What happens here? For that matter, I should really look at the control register. Okay. So that does select the faster clock, like it's supposed to. We should then be disabling RC2 and enabling RC32. That's what this next line should do. Which it does. This next bit should then enable the PLL. Are we still on the faster clock? Yes, we are actually. So PLL source is now set. And that's still correct. We're then going to try and set... What does that bit do? That's an OSC? Yeah, that's an OSC register. Oh, that enables the actual PLL itself. Got it. So we load the value that's there. Should be expecting to see that bit there change. Bingo. And because of the timescales in question, it's already ready because we're running so slowly for it. No, I did not want to use the USB controller here. I wanted to look at the... There we go. Clock cell is still correct. So we're looking for a write to the USB control register, which is offset 4. Right there, I think. Bingo. So at this moment, all the clocking should be set up correctly. USB worked, but we're looking at why I was getting the wrong clock frequencies out for the UART. And I think if I let this just continue right now... Yeah, I'm not worried about the PLL. What I'm looking at was... What I'm looking for is why the last time we were here, the system clock selection bits here were 0. The last time we were at this line of code, those bits were 0. Which, well, there's my problem. Well, what I'm inclined to do right now, Steffi, is I'm inclined to go and grab another USB cable, plug my, Glasgow in, and see what we get out if we allow this to just continue. Especially now we've got a breakpoint set. It's way down here somewhere. Anyway, we still have a breakpoint set for the middle of that clock code, so... I've gone back up too far! Anyway, let's get the Glasgow plugged in and figure out what on earth is going on. So I think it's that one that I want. Except I don't want to use the PTY. Oops. Well, close. I would like to be using the TTY in this case, because I don't need it to go to an external console and terminal emulator. I just want it to just dump to my current console. I have dead USB ports around. This is very annoying. You've got a USB port there, and stuff strewn across my desk. So if we do that, and then we... Interesting. You mean what virtual machine system am I using? I'm using VirtualBox. It's supposed to be screaming. It's my screaming UART. That looks remarkably close to 2 megaboard. VirtualBox isn't that bad. Beats out quite a lot of the competition, let's put it that way. And I don't have an ESXi host around because I'm not made of money. VMware is the paid alternative and it's kinda crap. Yeah, but that requires I actually go and know how to set up KVM and libvirt, and I'm not good with QEMU, so let's not put me through that. So, okay, I'll put it this a slightly different way to you, Steffi. It requires I basically have to do my day job at home because even the GUI isn't really automagic enough. It doesn't do enough of the heavy lifting for me. I still have to prep all the right files and... yeah, there's a whole lot of extra guff involved that just... nope. Whereas with VirtualBox, it's basically point and click, and actually I copied my virtual machines off of my other machine. So this is a virtual machine I've had set up for 3 years. Oh, Derek, I use QEMU too if I'm pushed to it, and my other half uses QEMU. I have nothing against it, but I don't want to have to do my day job at home for a project like this. And that's fair enough, Steffi. But it's about knowing what the right tool for the job is, and also how many spoons you're about to burn. For me, that's a very high spoon burn thing to have to deal with. I have not had a good time with libvirt. Ask me later. So, curiously enough, right now, I think if I configure... Steffi, it has been very close to my experience, and especially if I really want to get like KVM working properly, yeah, that's the reason I use VirtualBox. Exactly, it works with VirtualBox, is what I've got set up. Yeah, anyway. What I'm thinking is I might well actually try and get this to read out now with my... yeah. Might try and get this to read out now with my Blackmagic probe and see if we can get that wiring harness to work, because it looks like it should. In theory. I'm just setting things up. So I disconnect Glasgow. Which I ain't gonna like. Glasgow, please stop. Do that. There we go. Good question. let's just say that some of my experiences, Steffi, are very much tarnished with the brush of SLES in particular. Don't forget, I work in an environment full of crap. And we use this because the vendor supports it. All hail the vendor! Okay, that's got... yeah. So if I do screen, dev, tty, no, not ACM, bmp, hard, that's what I'm looking for. And we just continue where we were. Interesting. Am I using the right cable? I've got two of these cables made up, one of which is pass-through, the other is crossover, and the crossover is the one we want. Guess who's using the wrong cable to connect to the target? Whoops. Easy fix. Ow. When I can get the plug to go in the socket. There we go. Are you okay there, screen? You shouldn't be terminating like that. Hey! My screaming serial port is working. So, if we try this again, but this time we just run it to where we've done the clock setup, do we get the same answer? No. No, we do not. So interestingly, one run through we get the right answer, one run through we get the wrong answer, depending on whether or not we've single stepped or we've just run the code. How curious. So if we single step all this code again, which is going to take a moment, that's fine. we take note of what a good run looks like, okay, so this is a good run. This is what a good run looks like, and then this will just work from here. So the key values I need to note are state of clock cell, I'll actually make this so you can see what I'm typing. So that's a little more interesting. Just quickly move the virtual machine out of the way for you. And that's USB control. What's the oscillator config? How's everyone doing, by the way? Oh no, that was 1A, not 50. Well, this is a good run. This is what we know happens when we get a good run. So, what's different when we do a normal run? Let's find out. Oh, there are already some very intriguing differences in here that I can see. Let's just copy these values back out. So, control that goes to 0. First registers is 0, that's a 1 like it's supposed to be. We then have B. C0, 0, 0. Oh, interesting. C3. So the two main things that are different are the oscillator status registers here, XOSC fail, and then the resulting clock control register value, which all the registers that are different that are important are backed by these CCP writes. These CCP writes are happening too slow. just considering options here as to how to try and rectify that. I really don't want to have to drop into assembler, but I might have to. Too many instructions between when that register's being written and the register that's trying to be unlocked for writing is being written. Which is typically an optimizations problem. It shouldn't, but also the IDE knows that I'm trying to unlock a register for writing, and in order to get some of that information it's displaying in like the CPU pane, it's actually having to run some code on the CPU. It's having to, in a temporary area, run in RAM, run some code on the CPU to get it to tell the debug interface, at least I think this is how it works, key pieces of information like the program counter. So whenever that's done, and it sees that CCP has been written to, it has to redo that write itself before letting my next line of code run. Which I'm betting is the reason why it works in single step mode, because it doesn't realize that the CCP would be about to time out. So it's doing this right for me. I'm running the next line of code, and so it works in single step. No, it works because the debug tooling is accidentally making it work. It's a timing bug. The compiler's not doing anything wrong by having put quite so many instructions in to do all these writes. As such, it's a mix between I haven't got the optimization level turned up quite high enough, clearly, and the what's his name? You get the idea. Debug tool shimming its way in there, doing some stuff. Have I pulled out the flag debug yet? I'm going to try and fix this in the build system, so you got to watch me write a little bit of me song. That was not the license file I meant to open. So what we're after is, yes, I've done the debug flag. Optimization. Yeah, optimization is currently set as no optimizations at all, and I think I need to set it to G in debug mode and mandate a minimum of 1 otherwise. Actually, it's just single equals because this is an if statement. No, it's not the compiler. This is the IDE. This is the debug tool. This is the JTAG ICE combined with single step debugger. No. I'm saying the reason why single stepping works... I think we might be talking cross purposes here. But what I'm trying to point out... Oh, no. The reason why the original program doesn't work is just simply because I haven't turned optimizations on. This code needs an optimization done to it, and the compiler is not being allowed to do any. That's what O0 means. Do not do any optimization passes. I bet it will. But what I actually want to do, because I want to keep it debuggable, is I'm going to turn it to OG, which is debug-friendly optimizations. What I'm thinking will happen is that we'll end up with loads going to different sets of registers for where it's currently doing this LDI, MOV, STD thing. This sled of instructions should get elided somewhat, so we end up with two pairs of registers, let's say R22, R23, R24, and R25 loaded with the two different pairs of clock and OSC base addresses. Then we get a MOV and a store, so an LDI, a MOV, and a store, LDI, MOV, store, and that's fine, that will work. Because that's less than 4 instructions between the store and the next store. Yeah. It's because it's not doing that at the moment, because it's O0. That's the problem, I think. Yes, I agree, Steffi. But you're writing protected registers. We're gonna stop you from doing that by accident. Lest you get rogue code running. Which is fair, I guess, but also you should be putting a stack at the beginning of memory, maybe, so that you don't get the rogue code problem, and maybe just write better code in the form of code that has more checks in it for bad state and won't compile if it can get into those states, i.e. correctness by construction. But I know that that's hard. It's not an easy problem to solve. I'm just looking something up in Meson right now. I'm looking for... I think it's add project arguments. Yes. Because I don't think I can do a set option. I don't think that's a thing. Yeah, no, I can do set variable, I can't do set option. So what I'm doing here is I'm saying that we will forbid the program from being able to be built at optimization level 0, and we'll do that by saying if we're in debug mode, depends on the manufacturer. I've seen both, and not just from Atmel. So what we're doing here is we're saying if we're in debug mode and the optimization level would be 0, set it to debug friendly optimizations. Otherwise, if we're just in optimization level 0, force it to 1. And in theory, that should work. It won't change what's showing up in Meson configure, but it should change what's going into the Ninja build file, which if we quickly open that and I'll do a build, it should change things. Let's find out if this worked. target of assignment must be an ID. That's because it's not supposed to be an assignment. Oh, apparently it doesn't like me doing compare against an integer with a string. There we go. So if we look now, yeah, we've now got OG being inserted into the arguments here. How is this linking? Linking also needs fixing. That's easy enough. Bingo. So... I'm going to stop the debug because it's now out of date. The new code on the board should theoretically now be done. So if we look at the disassembly now, let's scroll down to Oskinit, there we go. Yeah, you see, this is so much cleaner. We can see there's our setup for the OSC registers. I think it was. Yeah, those are the OSC registers. And then set up for the clock registers. And we see much cleaner chains going on here. So, for example, load, store. It's changed something here to an out instead of doing a store. Load. Add to get a value that it needs. Store. I'm just trying to see, where can I find one of the rights to... Let's find out how this debugs. I've got to go and find the right entry point again, but shouldn't be too bad. Looks like it's... Run got put way down in the code. Well, that's kind of annoying. Out of my way. Let's put a breakpoint then on the return from Oskinit. 34C. Yes, that's correct, Dave. Or David. I don't know which you'd prefer to be referred to by, actually. That's a good point. Fair enough then. I know some Davids who get very touchy about being referred to in the wrong form. I am looking for a very particular instruction sequence and I'm not finding it. Ah, there we go. That looks to be the return. Yeah, that's the return from Oskinit right there. Let me show you what I'm looking at. There we go. So I've just set the virtual machine up so that we should be able to single step over to, or not single step, sorry, run through the code, just normal run through, to down here and see what the hell's going on. Loads of regex parser. I do not need a regex parser. Yeah. There we go, that's what we were looking for. And what does this say? Hey, we're on the right clocks! Oh, jeez. I'm already a pattern matcher. I'm a human pattern matcher. It's a thing, okay? The only thing that's not nice here is that if we go back to the oscillator settings, for some reason our RC2 meg is still wrong. But I'll take it because I'm willing to bet if I just run this, oh my. Yeah, that works. That's a lot of ah. I'm gonna turn off the screaming now because we've got that working. I'm happy with that. Oh, the scream, the scream. Sure. Oh, jeez. I approve. Right. I just got you rebuilt the firmware. It now won't scream at us. Might do other things, but it won't scream at us. Let's see, is the breakpoints we've got set? Oh, are the breakpoints we've got set still valid? Probably not. Where are the breakpoints we set? Okay. So 101. I really hate that this is all divided by 2 because it makes trying to figure out where we are in difficult. That'll be our run, I think. Alright. let's do disassembly and oh, we're not yet far enough down in the code. Grr. .282, I think it was. Yeah, there we go. That is indeed the first line of run. If I put a breakpoint there, we should see the clocks come up correctly. And we should then be able to monitor what on earth goes on after that. There's nothing. Yeah, we still have this RC2MN problem. But we are on the correct clocks. So I'm inclined to not worry about it. Yeah. So that's what it makes of the statements that are supposed to be coming out off of the UART now. Welcome, Hex-chan. It is... Well, we figured out what was causing the clocking to go wrong. And fixed it. Now I've got other problems. Like, this is all garbage coming out of our UART right now. Even though it shouldn't be. Hey. So I've got to go track down the UART write code that is trying to put values out and figure out why it's going wrong. Which... Let's do a little cleanup. And I'm also going to unplug the keyboard for a moment, because I need the USB cable for it out my way so I can type properly. I think it's safe to say we don't want to do that. I think now we've got it working, we do not want to lock the clock control registers in case we need to, you know, modify them at some point after this code has executed. There's no point me doing that, so let's get rid of those lines. The next thing we need to do is add those lines to the build system permanently. Oh, jeez. Yeah, you could do that, I guess. Not sure how happy it would be at you, though. Oh, it's doing this thing to me again. There's a view mode thing that it's gone and done. Oh, welcome, Obliterous. That sounds like you're having a great day. Sarcasm, of course. I know what's happened here. Oh. So I had my config for VS Code go and reset itself recently, which is why it's not displaying my version history here the way I like it, where the uncommitted items, untracked items are separate. And I'm trying to remember where the command to change it is. Should be in here though, when I don't accidentally click away from the thing that we're trying to do. Okay, this is annoying that I can't find the setting. Looking on my laptop real quick. User. Nope, that's not got my setting either. Oh, well, that's annoying. There it is. Yes, it's unable to write that far right at the second because I have it chunk chattered. It's marked immutable. Okay, sorry about that. Oh, that's so much better. I can see the wood for the trees now. Fixed the clock and the oscillator bring up issues in debug builds. I don't want to commit that yet, because there's a better way to do what I'm doing in there. Right. I split out a whole pile of stuff into a separate header. We need to add that header. Before I do that, I need to add string view. Implemented a rudimentary string view. Looks cracked. So this is a refactor I did. Refactor out some of the UART code. Into its own header. Okay. We are getting very, very close to the point where we can actually start trying to debug stuff again. I just need this code so that if we go modifying it, we know what we've modified. Because rule I have is you make the minimum number of changes in one step as possible so that you know what you've changed so you can observe the effect more clearly. It's going to take a moment to add all the bits. Oh my goodness. We know this code works because we've got the debug UART working for values of working. So this commit is initialize the debug UART to board. I need to deal with that one at some point, but that's fine. Okay. So the piece of code that I'm looking at here that I think is broken is, well, this, actually. I think this is where the garbage we're getting on the UART is coming from. So we are going to, in the disassembly, go and look for this function, if I can find it, and see if we can breakpoint it and figure out what's going on. So, oh, it's actually not too bad to find. It's this one right here. In theory, yeah, this UART write is calling this function up here. It's a lot of stack manipulation. Curious. Well, let me quickly replug the board in. And and let's find out what's going on in there. I also love how it thinks that the board is still running code. Nope, not even close. Right. So this will be at 1... what will that be? Brain can't do hex right now. 1 AC divided by 2 is not something that rolls off the top of my head. Sorry, 2 AC, not 1 AC. One 156. Okay. So let's find out what's going on inside of the UART at the end of each iteration. No. I want to know what's going on going into the UART, don't I? So I want to break on that line. There we go. And this is UART E1, I think it is. Yeah, E1. Okay. Call stack is absolutely useless. Oh, of course it is. Let's get rid of some breakpoints that I've just noticed are straggling. There we go. AB0 is the UART. So that's the UART to use going in. That is the apparent data to use. Oh, I know exactly what's happened. Oh my god, this is annoying. This is the exact same problem we hit with the LUT table. Flash reads aren't being generated properly by the compiler. So Y here we can see is currently 0, which is wrong. Y should be... Let's go and have a look at the stack. We'll do quite nicely. 27F6. Interesting. Trying to work out where the data that comes into this function is on the stack, etc. I'm also trying to remember which direction the stack grows in on this architecture. Because there's a lot of data in memory we can see right here. One of these has to be the return address. I know that. Let's try USB init. Should be 7E0, well 7E4 on the stack. Oh, pops. 6 pops. And then that should be a return address, but that's clearly not. Oh, we're not down at the call register, at the call site yet. That's right. Okay, so everything has become into this function. Duh. So, where's the return address then? Okay, stack goes downwards. Good to know. Yeah. Well, that means I need to convert 734 hex to decimal divided by 2. Aha! E9A. So there's our return address right there. Brain is starting to hurt. Okay, so Y is being loaded with 1400 hex, which is, surprise, surprise, uninitialized. Oh, hang on. Why are we in the data set? Okay, so it should be initializing USB. That's what should be there to be read out. I am betting that is not what's about to happen. This should be calculating the end address. Yeah, so we've now got our end address here as 1617. Huh. Oh, I see. We do a jump, we then do some compares. We branch backwards into the loop. R22, that's where we're going to load this value. And we load a 0. That was supposed to load 49. Yeah, it is the bug I thought it is. It's not doing a proper flash load. It's trying to use... It's making the mistake I made in the addressing here where I was stuck in the data space. If I do that, that's a different address to this. Because the compiler is being a derp. Yay! So, what that's going to practically mean is this needs decorating with the flash stuff that we wrote. And I need to actually commit all that code. I remember why I didn't yet. Yeah. Okay. Just thinking through how I might work this. I knew I was gonna have to do it this Sunday. Yeah, because what it should be doing is using ELPM rather than using... How to make this? Because the way it's doing it is actually currently not standards compliant, which is why I didn't commit this code. So we convert into a pointer, guarantee that we have a pointer. We then need to have a result variable. So the first thing it's doing will actually be this one, not the enhanced one. Read into a temporary register and 2. That's what this line would be doing. Having grabbed ramp Z, knowing I need to reset it after we get done. And then output to the ramp Z location, which is 3B. The highest byte of parameter 1, which is the address that we want to read from, which we'll call value in our code, because I'm going to do something similar to up here, but less hacky. Mov W into register 30. I don't think I get a choice on that because that should be the Z plus register. Pair the address of, well, the value of value, which is an address. One of the few times that reinterpret cast is valid is to do it in this instance where I'm trying to convert from a pointer to an integer. This will give me an integer that can be converted back into the pointer, but in our case we're actually going to pull it apart and use it here. That'll be the easy way to do that. Nice, you wouldn't put a T long enough. It is not. You and 32 tiers, so we'll do that. Alpum into the register holding result. Whatever's at Z plus. And we are clobbering registers 30 and 31. It's not pretty, but it'll do the job, I think. Why not have enough colons? Colon for that one. Colon for that one. Colon for those. Yeah, that should be fine. Oh, okay. Yeah, it won't know quite what that is. That's fine. In theory, that replaces that with valid C++. Well, more valid C++. Which will know if I've broken something if I try and run the LED code and stuff runs badly. So I'll just do a quick run of that and see what happens. It should work. We shouldn't have a problem. I do need to disconnect the debugger. So I can do a Ninja program. If my JTAG ICE will talk with my... Oh, interesting. Upgrading the firmware on the JTAG ICE when I had to do the upgrade of the firmware broke AVR dude. It can't see my JTAG ICE. Ah! Never mind, I'll reconnect the debugger over here then, and we'll do it using these tools. Now, that would also do it. Whoopsie. I left the keyboard disconnected. Try that again, having plugged the keyboard back in. How's everyone doing, by the way? I hope this is still somewhat enjoyable for you all, even though it's a bit of a struggle bust. Okay, that looks like it's okay. Oh, fair enough then. It doesn't look like anything too crazy is happening as a result of this change, so I'm happy with that. Which is good, because I'm about to need to use this in some really nasty ways. Which also gives me hope for this code. I'm just trying to work it out in my head at the moment. How do I tell this that the whole thing is in Flash? I think I want to make a specialization of Flash T that allows that to work. Yeah, I want to do a specialization of this. That's what I'm gonna do. Which means that what does that actually mean? It means that we need to implement operator square bracket. And operator add and operator let's try the first time. Operator square brackets, operator add. Fair enough. Oh, an operator star still. Okay, so it's 3 operators I need to implement. There's UART operator star. Just takes the pointer that we have and grabs its address, does the same thing as before. Flash T UART star. Just noticed something that I'm going to have to fix before I let this compile. This is now going to be char star there. This has got to be char star. Haha. That's going to be fun. This code's almost the same, but a little tiny bit different. Good thing I caught that now. There we go. So this is flash T char star operator plus taking a size T. Yeah, size T. Which is going to in place construct a new flash T with the value pointer we hold and the count added together. It is essentially the same as the raw operator was doing anyway. So and we can mark that const expr, which is nice. I think the operator square bracket, that was the other one. Yes. The only way that could be worse is if you'd said and you were using Code Composer Studio. Helps if my fingers aren't off by one. I want to move this operator up quite a bit. Move it all the way up there. I think I can do that. What I'm doing here is I'm computing. Well, I'm invoking this operator up here, and then from the result of that, I'm then using operator star. Although I think that's probably slightly nicer. Yeah, a direct call to the operator plus of count with count as the argument. And then dereference the result, run this. Yeah, that works as, I guess, as a way to do operator square brackets. JUnit? Oh geez. Why are you using JUnit, which is a Java thing? I'm intrigued. It does not like that I've just gone and told it to do const extra stuff with non-const extra calls. Like, this is not const extra anymore. I think I know how to make this work, actually. These need to be marked const extra. But they can't just be marked const extra. I need to do something special for this. If const extra stood is constant evaluated, return star value underscore. There we go. Else, well, yes, I know that code needs to go there. Visual Studio Code. Thank you. That should put this into a non-const extra context. That leaves me with only 2 errors. Const extra bool operator equals, and then operator not equals, and also operator plus plus. And then this operation... I will format this way more nicely than that. That's horrible. Also, it's value underscore, not underscore value. So this just simply goes and iterates forward only. Well, allows forward only iteration by allowing you to increment the internally held pointer here, and returns itself. I might as well implement operator minus minus while we're here, because it's easily done. That allows forward and backward iteration with this type. Yeah, I'm okay with that. Firmware builds. This is generating a lovely warning about tautological comparison. But that's okay. Let's just see if that worked first. I need to do a disassembly. Oops, wrong window. So if we look now in UART right, interesting. That didn't change the code gen. Oh. It won't have changed the code gen. Because it's as if that flash type isn't there right now. Okay, I'm gonna get out the const expr logic again. I'm gonna just remove that. Because obviously that's causing us problems. And we'll go and fix these warnings, or errors rather, instead. It should be a little better. Actually, I keep changing what I'm doing here a little bit because I'm trying to work my way through a kind of a laundry list here. What's actually probably better to do is going to be have a FSV, which is a flash string view operator, which is non-standard. We then grab that and copy it. Got our normal string view here, which is const char star string pointer is a const char star, iterator is a const char star, that mostly puts everything in place ready to go. And then we have a flash string view, which has the flash stuff in it, and we stripped the const expr out of this one, because this is the one where we know that the strings are going in flash and we can't do anything about that. We take a performance hit when we want to do, well, we can't use these strings for compile time things, which is fine, because then we're indicating intent anyway. And that means this will need to take a flash string view. And these here need to become flash string views. Front can't return a reference here. I'm okay with that actually. Reference types don't make any sense on this, so this is char front, char back. Iterators are fine. Pointers to the data are fine. And that'll be a char. That is size T, but okay. String view operator FSV. That'll be invoking this. Trying to work out why I'm getting some errors I'm seeing. Oh! I know exactly why. Oopsie. I forgot to put change signature into the header. Compiles and links. So now, there we go. Here's the code that goes and pulls out data from Flash. Let's see what that does. Plug the keyboard in always helps. The tool isn't disconnected. Oh, you know, yes it is. How many times have I done that tonight? Jeez. 1 AC was... Sorry, 2 AC rather, not 1. One, 5, 6. So... That looks like that's... Yeah, that looks right. Okay. Well, this could be interesting. Looks like things got shuffled along slightly in Flash. I'm trying to work out where that is. C minus 4, 8. There we go. Should be 1418. It looks like that's where we've one of the values we've got in registers here, so and that looks like the end. Register 22 is the one to watch. And there's a 49! Hey! I wonder if this will just work now. We'll put everything back having done that. We then loaded the UART to use. Yeah, that actually worked. Holy crap. I'll pause that and I will fix a thing in the code I've just spotted as a result of this. That works! Color me slightly surprised actually, because I wasn't quite sure that this was gonna work. I forgot to put any new lines in here, which is showing on the UART because there are no new lines. So, do that. We disconnect the JTAG ICE from the VM again. And we do that, but I'm also going to have VS Code listening on the UART. Will ya look at that? Cool. That's what we want to see. So I've got to do some sprinkling now of some more. We can actually finally get back to the topic of, yes, of last week's stream. It's taken us 2.5 hours, but we can finally do it. We can now sprinkle some more debug rights throughout the USB code, being careful about how long that causes us to take to get through any given block, and we can kind of get an idea of what's going on. Welcome back. You have come back just in the nick of time for me to get debug UART working. blocks are working. UART is working. If I actually just do that, there we go. Now we get proper new lines in there. Yeah, I forgot to rebuild OBS before I started streaming, like a doofus. So we get no nice overlays because the artificial version of OBS doesn't currently have the web browser overlay stuff enabled. So I have to do a custom build every darn time. That would be very much appreciated, yes. Also, at this juncture, I'm going to hit the big pause on this virtual machine because I don't think I want to leave it running unless we end up needing to debug things again for right now. This is going to take a moment or two to pause and spin down. Oh. And there goes my poor disks trying to sync all this data all at once. RAID array is feeling a little bit right now. Oh no, Live Audio will just keep going as soon as it gets the ability to read data again. Oh, it's not the Linux IO stack. This is the fact that I am literally writing gigs of data to my RAID array. No, it's not. It's ZFS. It did. But we exhausted the queue before it could go and pull more data off my pool because the big giant write was being given precedence. Oh no, it was more than a couple of seconds. That was 5 to 10 seconds of audio that we were hearing before it went, oh, whoops. ZFS prioritizes the write over the read because it wants to get that data onto disk as quickly as possible. That's its prerogative. It's not a Linux thing, it's a ZFS thing. It's not terrible for doing what it's designed to do, which is to protect your data at all costs, so you get the maximum uptime and reliability. Yes. ZFS is designed to give you very high reliability, very high uptime, at the expense that reads may be slow. Data integrity reigns supreme in ZFS. So the write takes precedence because it needs to get it done. It does make sense. It is, though. That's the whole thing. In ZFS, it is. What if in a second time... No, you can't. What if you're in a business, in a second time, the power goes out? And you just lost thousands of transactions because your file system was prioritizing reading over writing. That's the problem it's solving. If that second is a difference between you getting all your data It is in ZFS. If that 1 second is the difference between it being able to write down all your data to disk and preserve your business ability to function, and data loss, it's choosing that second faster. That's ZFS's prerogative. That's how its scheduler works. Anyway. I found that kind of funny. F-Sync's broken. That's the problem. F-Sync is completely broken throughout the entirety of all Linux file systems. Most assume that nothing goes wrong. At best, the guaranteed behavior of F-Sync is actually data loss. If you've got a failing disk and you do an F-Sync on ext4 file systems, it will lose your data. They can't do better. They've tried. There are entire kernel threads on this. Smarter people than me have gone, I don't know. No, even if you've got blocked-based checksums, that's the problem. Disks lie. Disks lie, and caches are a problem too. The problem that you hit with ext4 is it has... yes, but it is Linux's problem. Oh no, even the Pro disks do. Even the Pro disks do. In fact, they lie more than the normal ones. You can have that argument with machines up the road from me. I've caught them lying. And we buy Pro gear. We have to buy Pro gear. And I've caught them lying. Not my file systems, not other sysadmins. I've caught them lying. It's great. Whole thing's a shit show. I wish it wasn't, but... So F-Sync isn't just a sync instruction to the disk. Things are more broken, but you don't notice it more often than not, either because error recovery mechanisms kick in and get your butt, or, you just get lucky. More often than not. Oh, welcome back, HexGen. Yeah, Google for F-Sync gate. It's bad. In the edge cases that ZFS is interested in protecting against, there is just no other option than to ignore the way the Linux deals with things, to override how disks normally view things, and to prioritize writing over everything else. It's really shit, but yeah. ZFS wouldn't exist if disks didn't lie, basically. ZFS runs many heuristics in the background, along with constantly analyzing the smart data of the disks, etc., to prioritize which disks it's going to write specific data to, and even move data off of disks that are currently failing for you transparently. Because it can detect that before you can even see that in SmartCTL. Because it's doing long-term tracking. But fsync doesn't just do a sync to disk. What it does is it actually synchronizes a whole pile of file system structures with the current state of the file system and then writes them all down to disk. So it doesn't just write your one file to disk, it writes like half a dozen files effectively. And I've been on the unfortunate end of a failing disk in a professional environment where that has actually occurred, and I have seen the two terrible lines of, I couldn't write this structure, I'm just discarding the structure as if it didn't change from ext4. That is its fallback behavior. It discards on fail. And it's not the only one. ext4 is actually really good. The journal is good. The journal did recover that file system. We did lose a file, in terms of we went back to the old version of the file, but we didn't lose anything else. The journal did save us, but not good. Because if that was a database, I've also seen that happen on XFS. ext4 is nice by comparison to NTFS. Right. Yeah. On me. Oh, hang on. We enter into reset here. Suspend happens, but we go to attached. Waiting, because we come out of reset there, we immediately do another write to state. So this should be possible to enter. Windows is a worse, Mac OS is a worse, and all the IO schedulers are shit. But it only works on certain disk types.
Drop the crap.
Funny for not getting performance how we're able to do 20 gigasecond I/O using Lustre on spinning Rust. That's not even the peak throughput either, that's nominal. That is random I/O performance. Supercomputers are fun! No, I'm talking of 20 gig spot performance. Oh, yeah, I know. We are talking several racks of discs, yes. But you can get performance out of spinning rust. Oh, that's cute. Each one of those file systems has 1,500 disks in it, if I recall correctly. It depends a lot on the file system and the backing hardware, etc. These are using dedicated hard drive controllers, RAID array controllers, and it depends. My RAID array as well gets gigabyte performance peak throughput. And that's just 6 spinning rust disks. The ones you can get your hands on normally suck, yes. These RAID controllers are dual redundant and are quite special. They're also a giant pain in the ass to admin, but that's a slightly different problem. I agree, I trust ZFS more. However, I've seen some shit. No, actually ZFS is capable with some tweaks, and the right file system running atop of ZFS to get some pretty insane read-write speeds, but again, you're into the many disks with very specialized hardware. Google the name DDN, Direct Data Networks. Interestingly, we never enter into the IO interrupt routine. That explains why we're seeing the behavior we're seeing. That's fair, Blip. Oh, there goes my neck going crunch. So reset here should be setting up and enable... Yeah, we enable the IO interrupts. This is going to be interesting to debug. I might actually go and attach the Windows VM to it again. But I'm going to give this a shot first. Where is the USB controller again? There it is. Oh, I wonder if our endpoint table isn't properly aligned. Align as or align of? That's the question. CPP reference to the rescue. This is a language feature. Line as? Align of returns the alignment, so we can actually do an assertion. Which should be fine. Oh, with non-type. Really? Maybe ask it what the alignment of a given type is then. Oh, not type, sorry. Value. Oh, whatever. I'm just gonna trust that for a moment, that it's correct. Now that we've put that extra point in. I need to reset my USB hub again. My mouse is now not working. Hello. That's interesting. Oh, I bet that's because I left the keyboard plugged in. Yeah. Keyboard was making angry. Okay, I'm going to open Wireshark then, and we're going to have a little look and see what the traffic is now showing for the keyboard. And I learned something recently that we actually want to be looking at USB Mon 1 because this is on USB Hub 1. So, this way we don't get quite so much crap coming in. We're still going to see my mouse because it's also on the same hub, but interesting. It gets stuck. And we aren't seeing it go into reset here. Should be hitting this line. But it's not. So, let us jump down to try and make sure I understand how this code even works. Three, 1/3 VA divided by 2. Whatever that actually turns out to be. $9DD, apparently. Oh, interesting. This assembler does not like that. Oh! I just spotted that it's dividing things by 2 for me if I put the actual address in. Bingo. We probably landed in the middle of the data region or something like that then. Bingo! Anytime it wants to actually go into that interrupt routine would be great. We've got XCIF. Oh, this is the UART, not the USB stack. There we go. Enable speed. Max endpoint is set, that's all good. We are attached. Okie dokie, take care, Steffi. Ah, we have been bus suspended, that's not really part of what's going on. Let's have a quick look over in the table. 29FC. It is, yes. USB EPT. There we go. So each one of these should be representing a status value, a control value, 16-bit counter, 16-bit data pointer, 16-bit aux data pointer. That's what that should all mean. I'm seeing some very spurious values in some of these registers, so I wonder if yeah, we need to complete clean house when we go and do the iteration of these endpoints. they are getting trash put in them, and that's why trash is happening on the device. Yes, exactly, Obliterous. 0. All the things. I'm just gonna double check the meanings of various things. So this would be endpoint.status is 0. I also should set up the endpoints. Oh no, that's fine actually. So the status registers need clearing. The control registers should actually be okay. However, the count value also needs resetting. Data pointer will be fine because we set that up manually. But we also need to clear out aux data. Bit like that. So let's give that a shot. And I'm actually going to plug this into my laptop this time, so that the USB stack on my desktop doesn't freeze up. If my laptop will allow me. Yeah, my laptop will allow me. Cool. We'll need to do another disassembly and find the IRQ again. It is a 13848. Excellent. Keeps moving. We want 13C4. It's the instruction we want within there. And actually, the other thing I'm going to look at is USB init. Let's go and check the state that it leaves everything in. That's... Oh, there it is. I'm like, why didn't it put the function at the very top of my screen? You will never know. see, it's doing a write to control a write to the endpoint pointer. It's like 75C is the actual instruction we want to break on, so that we've already done some initial setup of the USB controller. So we've got enable, speed, max endpoints. I'm actually going to put that over there, so we can kind of track along. That's easier. So that's set. Control A up. The endpoint pointer is set up. Interestingly, everything starts out 0. Oh, interesting. Oh, because it's in VSS. So my startup routine is zeroing this area out as it comes up. Okay, so there's the first data pointer. And then the... Let's go and pull the right file open. Oh. I hate Visual Studio, if anybody couldn't already tell. I find it horrible to deal with. Okay, so storing zeros there. That's what happened with those two lines. Another data pointer tells me that the data buffers are about here. Okay, so we've set up 1, 2, 3, 4, 5, 6 areas, but we're only going to use 4 of them for right now. Let's see what that looks like. Okay, so that's setting up the... Oh jeez. That is quite funny though, as you could probably tell from my before. So we set up the first control word. There's the second. There's a stalled endpoint 1 out, and a stalled endpoint 1 in. Yeah. We then do some more shenanigans with setting up masks for interrupt control registers. Including making sure that our address is set to 0, which it is. Excellent. Set up Control A of the interrupts. So we've got bus interrupts enabled and an interrupt level set. I got that. Big Ban Hammer. So, yes, I did. I think we're now setting up state here. I think these basically all turn out to be zeros. Okay, that was a lot of things to suddenly... Oh, I see. Right, this should be in the routine that's handling IO completions. So the first thing we're doing is doing a load. Should be for the status bytes. 24, so it's 0. That doesn't make sense actually, it shouldn't be 0. And I'm really sure that that is the status value that I've just read in, because we then do an and another and. It's 1, 3, and what register is that? Us. Oh, I'm looking at the wrong datasheet again. Where's the USB controller? Where's the UART? Oh, USART routing. above TWY. Where's it gone? Table of contents, that will do nicely. Oops, when I don't click on something in the TOC rather than clicking on a specific item in the TOC. This is almost like I'm looking at the wrong datasheet still here. Oh, it's the AU manual. Okay. So I was kind of looking at the wrong datasheet. That tells you how much overlap there are between the A and the AU series. U will be USB. Endpoint description. There we go. So it's the status register. Yes, that's what we hoped for. And we are seeing hex 1.3. So toggle bus NAC setup complete. Can I go and... yeah, I can put it back on there. There we go. R24 is coming out 0. Huh. Oh! No, R24 is being loaded with the endpoint number. Is at 81F, which won't be 81F, that will be... what will that be? I really hate how they've made this extra difficult with the whole translation thing. It is jump to 10E 3E, which is handle control packet. Okay, that is actually where we want to be going. So clearly that 1.3 is correct and we're actually acting on it. This is in device. So the first thing that this routine does is it's going to pull packet direction info out, Test it for 0. It should get us into this block. Where we then do a load of the status register. I've just spotted a bug. I think I spotted the bug that is preventing us from answering. USB EP0 out is the incoming endpoint data is the one we're actually in this routine for, is brackets 0, and we've got brackets 1. We're looking at the next one along, which is the input endpoint to the PC. Let's go and fix a bug. Oops. I think I have this confused in quite a large portion of this code. So let's go and actually check everything. For the input side of things, that's 1 for an in packet. Welcome back. I am having entertainment. We think we might have found the bug that has been... Yes, it is. I think I found the bug that's been causing us the reason we don't respond to setup packets like we're supposed to. I have endpoints backwards in my head throughout all of this device code. Right here, we were pulling out the status value for the in endpoint, as in USB EP0 in, which is our outgoing data, the PC's incoming data. Which is wrong. We actually need to check the out endpoint, which is our incoming data. I hate the way that this is named in USB. Because this is the confusion it leads to. Yeah, tell me about it. So prepare setup packet should be on endpoints 0. To prepare us to receive a setup packet. Handle a setup packet also should be on EP0 out. That's a stall there for out. That actually might want to be a 1. That one actually might be correct. That's correct. Controller in needs arming. That data buffer's not one we mess with. Is it? No, that's not one we mess with. It's... That line's in the wrong spot. That's what's confusing me there. That should be here and doing stuff against the out endpoint. This is if we need to receive more data, it needs to go into our general receive buffer, not overwriting the setup packet. Hey, Hextran. Meow. Meow. Just slowly frying my brain here, as you can probably tell. So we are doing reads onto the right EP and writes onto the right EP. I think that should probably do the trick. There's 2 breakpoints. One which is currently in... Okay, that one can go. That one's the one in... here. Which we now know we're entering control packet. Handle control packet, and it's fine. Yeah, it's not a real Windows 10 machine, it's a virtual machine. Handle control packet has not moved. Yay! So this breakpoint is still valid. It should be coming back to me already. Oh, it's doing single stepping the whole second way, isn't it? Let's try that again. I think it turns my breakpoint off and then it starts doing single steppy stuff. Or it just goes off into La La Land. Well, whatever. I'm going to disconnect the keyboard from my laptop then, and we'll put it back on my main machine. Having disconnected the programmer from the virtual machine so that we can then do some VBox. Not VBox. Wireshark. I need to have set up in advance. Hmm. Well, it would help if it would allow me to reprogram the board. Which is what we're currently waiting on it to time out for. Frustratingly. I'm watching as it's trying a few times and it'll then finally let go of trying and go, nah, I can't talk to that thing. There we go. No, that was the first time out again. Hey. Wait. Did that just work? Which thing just responded? No, it didn't work. Ah. These here are from the JTAG ICE itself, which is also on the same controller. Just for extra confusion, you know? You all like to be confused. Yes, that was my hand going thump into the desk, sorry. Oof. Yeah, that's not a fun problem to have. Is that still failing? It should at least be answering with something. Well, there's only one way to find out. Well, yes, because I didn't yet plug the device into the laptop, so it's got no power. Oh. Okay. Yes, I have to pass through my JTAG ICE into the virtual machine so that the proprietary tools that we are currently using can see it and step through code with it. Because my host can't yet. I'm going to work on an open source implementation of the protocol that it's using to talk with the chip. None currently exists. But that's for a different stream once I've got a board made that interfaces with my Glasgow. This, however, is a problem because if I want to then just reprogram the board normally, I then have to redetach my JTAG ICE3 so I can then see it on the host and use it with the program command I wrote, which is actually right here. This, which just runs AVR dude and tells it, hey, go and put this bitstream on the board. Or not bitstream, firmware blob. Does that make sense? Hopefully it does. There we go. So, handle control packet is still at that address. Okay, so the breakpoint is set. I wonder. I stick a breakpoint in at hex 13 BC. This is in this is this call right here. I'm just making it so that the device will actually stop and then go, oh, really, you want to run that code? Okay. Hopefully that works. It doesn't seem like it's working. Should be doing the business for us, but I'm not seeing anything. Oh, for the love of... It's still stuck in the startup code. I don't know why it does this. Where were we breakpointed before when we successfully got it to go all the way through into there? Ah, that's right. We had a breakpoint as well in... USB init. Specifically, we want to breakpoint on its return here, I think. Well, actually, just before that, I do a right to control B, which kicks a whole lot of stuff off, so we want to breakpoint just before that right. So C6 looks to be favourite. Yeah, because this is me loading attach and then storing attach before we do a return. Bingo. Now it's behaving properly. And indeed, our space here is all set up nicely, and we've got like 287B is the area of data. Where's the memory windows stuff gone? Windows. Not watches, memory, there we go. This is 287B that I want to watch. Okay. What is it with breakpoints? Breakpoints that don't work are the worst, right? But we can see here that we've got something that looks remarkably like a setup packet to me. So we are getting data into the micro. If ever we can persuade it to run the interrupt routine. Let's then put another breakpoint into the interrupt routine. Right around where we load. We do that, which is apparently 1370. This is kind of frustrating, honestly. Break on my breakpoints. This isn't hard. Hey, we finally got somewhere. One of the breakpoints fired. This one is for 1370. Yep, that's the beginning of the IO completion IRQ. Should be interrupt B flags that we're interested in. It's going to first load the USB state information. Is in handle get device descriptor. How did it jump all the way over to there? That's a breakpoint in handle get descriptor. Oh, handle standard request moved. That's part of the problem. So, handle standard request. Oh, not handle standard request. Ah. Shite. Oh, no, okay. We are actually in... This is this multiply divide thing again. We are actually right here. Means if I look at... There's our setup packet. And a whole pile of other stuff that got blasted into memory there. Oh no, there's our setup packet. Of sorts. 1.3. So that's just generated endpoint. Okay, this looks like we're in the midst of... Yeah, that was it figuring out which direction the endpoint is. So we're now at hex 103E. Okay, finally, we are actually in the thing we wanted to debug, this. Have we received a packet? The answer should be yes. Yes, we have. No? I didn't say your name, but... It's cute that you thought I did. I'm dealing a lot with hexadecimal. Hence saying hex a lot. That's perfectly fine. You are perfectly fine. I apparently can't debug this. Because it won't let me breakpoint in the code I need to debug. Well, we actually have got a long way further than we were before. We have the UART debugged, we have all the clock control stuff debugged, and permanently fixed, thank goodness. And it wasn't that I wasn't understanding the datasheets, it was actually that the compiler was generating more instructions than could be run between doing a particular action which unlocks registers for writing and then actually doing the write to those registers. This at this point is going to be a struggle bust and an exercise in futility, I think I'll call this. Because I need to get it to tell me in here, UART write, debug UART. Actually, why am I using this rather than using my host? Pause that and get rid of it for a moment. So yeah, we need to know whether or not we are, well, yeah, whether or not we're getting here or not, we should be, and then what's happening within this, and thank you. My desktop is named Shiro, so yes, there are several anime which have that name used for a character. You can probably guess, though, from my desktop background, which anime I was intending when I named my machine. Yeah, it's going to be a lot of firing in the dark, and I think this is something where I'm going to struggle bust it off stream, because you do not need to watch me try and shoot at a USB controller that's moving faster than I can aim. Try and see what I can hit and find. Yeah, we've got a lot done though, so I'm happy with the results today. And next stream, I should have the key plate. Ah, fair. I'm going to do a soldering stream next stream, rather than hitting my head up on code repeatedly. That soldering stream, I would like to try and get all the LEDs finished, all of the LED drivers finished, because we actually don't have all of that done yet. And we'll see how far we get with the key plate side of things. Certainly, at least I want to have done a test fit of the key plate, make sure it fits correctly over all of the stabilizers, and we may even get as far as the soldering of the keys, which would be really cool, because then that means the keyboard hardware will be completely assembled. I may also make that an earlier stream than normal, because I know that soldering is going to take some time to do. So I'm going to provisionally say I will start somewhere around 4 UTC next week. With that said, thank you all for watching what has undoubtedly been a interesting stream, and I will catch you all again next week. With that, I wish you all a good rest of your day, and good night.